Hi everyone, hope you enjoyed the summit so far. In this talk, I'm going to tell you about VMware's journey with Druid, how we use Druid for networking and security analytics. First, a little bit about myself. My name is Bo-Fan Hu. I'm a senior member of technical staff from the NSX Intelligence team at VMware. Here is the agenda for this talk. First, I'll introduce our product, NSX Intelligence, and its applications. From there, we'll see why we chose Druid to be our main database. Next, I'll show you how our data is ingested to Druid. Then, I'll tell you about our 3-year journey of using Druid, where we constantly need to maintain a balance between cost and performance. Finally, I have a wish list that includes things that we'd like to see in Druid in the future. So what is NSX Intelligence? Imagine you have a data center where tens of thousands of workloads are constantly chatting with each other, or some machines or IPs outside of the data center. As a network admin, I might want to know what is happening in the network. Have we found anything malicious? How to keep the network secure? That's where NSX Intelligence comes in. It's a network and security analytics platform built into VMware NSX that can address these questions. So one application of NSX Intelligence is visualization. It can visualize your network topology and show you what's happening in the network. For example, each bubble on the right here can be a machine or group in the data center, and you have thousands of them. The green or red lines between them are network traffics. Some are allowed by the firewall, some are blocked by the firewall, and some are not protected by any firewall rules. When you hover on the lines, it shows the number of each type of unique flows that happen between the entities. This shows you how micro-segmented your network is. If you see a lot of red lines, then it might not be very well protected. If you want to see specific kinds of traffic like SSH, you can apply filters and it will only display those. Or if you want to see details, you can click on the lines and get information like ports, services, packet counts, flow end time, and so on. Another application is network traffic analysis. We have multiple detectors that can detect different kinds of anomalies. To do this, we analyze the flow patterns and build a baseline. When an anomaly happens, for example, some machine began to scan ports on another machine, which it never did before, we can detect these and alert the users. Now you realize there are unprotected flows or anomalies in the network, but how to keep it secure? You may have thousands of machines, and to set firewall rules for them one by one can be a chore. NSX Intelligence can recommend firewall rules and security groups based on analysis of the flow pattern and existing policies. So with one click, you can micro-segment your entire network. It can also continuously monitor for changes and recommend new policies. So those were the major applications of NSX Intelligence. Let's take a look at our data. We have two kinds of data. The first is network flow. It's a streaming data with fields like time, source and desk IPs, source and desk groups, ports, and protocol. And the flows are coming at a very high rate. We currently support up to 1 million unique flows per 5 minutes. The other is configuration change. It's also streaming data with fields like time, name, and type. For VM changes, you may have fields like creation or deletion time. For security group changes, you may have updated membership. And for firewall changes, you may have the source and destinations and the rule action, which is whether to block or allow the traffic. Now, seeing our applications and the data, you can see why we chose Druid. Both flow and configuration data are time series, and Druid is a time series database. The flow data has a high rate, and Druid supervisors are very fast at ingestion. We have different types of queries. Queries in visualization need to be interactive because the users will constantly click on the graph, and queries in recommendation and anomaly detection can be batched. Some queries are heavy and need to query millions of rows. Some are light and only query a few configurations. Some need to query the latest data and some query older data. And with more data coming in, we need to efficiently scale. Druid has a distributed architecture, so it's easy for us to scale. As ingestion rates goes up, we can add more middle managers and historicals. As more queries come in, we can add more brokers. Finally, Druid has enterprise support from Imply, which gave us a lot of help in the past few years. Before I start talking about our journey, let's take a quick look at how data is ingested to Druid. The configuration changes are streamed directly to Druid. For flows, we have a mini batch processing pipeline that constantly queries configurations from Druid and correlates them with the flows. The correlated flows are then streamed to Druid, where they are stored and then queried by the applications. We will get back to this diagram when I talk about some of the issues we faced. Let's start talking about our journey. As I mentioned earlier, we need to constantly maintain a balance between cost and performance. We want to support more data and more features, but the cost needs to stay low. We have two paths. One is from single machine deployment to Kubernetes. As we support more and more data, vertical scaling becomes expensive as cost for specialized hardware is very high. Moving to Kubernetes allows us to use common hardware and scale horizontally. The other path is from on-prem to the cloud. Running as a service allows us to provide more functionalities to the users, but we also need to save cost. The first version of NSX Intelligence was relatively simple. We had a single machine deployment, as you can see from the graph, not just Druid services, but our applications, streaming and batch processing services, they were all running in the same machine. We support up to 500K flow ingestion per 5-minute interval. We used local deep storage and had multiple supervisors, one for each type of configuration data. For example, one for VM, one for groups, one for firewall rules, and so on. We had two Druid middle managers, one for each type of peons. The peons for flows were larger since flows are coming at a higher rate, and the peons for configuration data were smaller. As you can see, there were no fault tolerance in deep storage, and we had high memory consumption due to the large number of supervisors and the extra middle manager. One of the things we learned in version 1 is reindexing. Suppose we have 500K flows every 5 minutes. Without any roll-up, they will take up a few GBs every hour and a few TBs every month. Since we are on a single machine, we don't want to spend that much resources. Luckily, our applications only look for the most recent flows, so we can perform reindexing and roll-up periodically. Our flows are originally ingested in minute or hourly granularity. Every day, we reindex the flows from the previous day to daily granularity. Every week, we reindex the flows from the previous week to weekly granularity. This greatly reduced the number of rows and segments, saving both CPU and storage. We made some optimizations in version 2 to address the problems we found in version 1. We are still a single machine deployment, but we changed to distributed deep storage and only kept 2 supervisors for configuration data. We changed to using only one Druid middle manager and set the configurations for the peons in the supervisor specs themselves. When we switched from local deep storage to distributed deep storage, we had to do deep storage migration. In the beginning, we performed deep storage migration while the streaming tasks were still ongoing. This created some problems, as the latest segments weren't migrated to the new deep storage, and the reindexing tasks were failing. So if you're doing deep storage migration, you need to be very careful and ensure segments in the metadata storage and deep storage are in sync after migration. If segments are accidentally deleted from deep storage, no worries. It's still possible to recover them from the historical segment cache. In version 3, we added significantly more features and data sources. We also enabled automatic compaction on all data sources to merge smaller segments. The first issue we found was resource contention. The new data sources and compaction jobs needed more memory. The new features needed more memory. Everything was requesting memory, and we were overcommitting memory everywhere and everything was slow. To mitigate this issue, we tuned all the Druid services. We started with smaller values for things like buffer size or thread count. Then gradually we increased them until the ingestion and query speed fit our requirement. Another issue was heavy queries. They were slow and blocking other light queries. We used Imply clarity to identify the bottlenecks, tune Druid accordingly. Also, we set query timeout and limit spec so the heavy queries won't go on indefinitely. We also added application level guardrails, which is like a simple query planner. If the application believes the query result would be too large, it will not issue the query at all. Also, we noticed that the compaction jobs were failing. After investigation, we found that it was caused by a lock contention between the compaction and streaming job ingestion, since they were working on the same time interval. To solve this, we delayed the start time for the compaction and added reject late message to the supervisor specs. Version 4 was a major update for us. We moved from single machine deployment to Kubernetes cluster. It made scaling easier, and we could support 1 million flows per 5 minutes after scale out. As you can see, as more flows come in, we add a new Kubernetes worker node, which will contain additional middle manager and historical. The issue with Kubernetes is we actually got less resource per node. Earlier, we had 128 GB memory in a single machine. In Kubernetes, the nodes are more but smaller. We had to tune Druid services again so they could fit into the smaller node. Due to the resource constraint, the queries also got slower, and the configuration queries were not getting enough time to finish before new flows come in. So we added a separate tier of historicals just to host config data. Version 5 was still Kubernetes, but we added more features including ML jobs. The ML jobs would query large amount of data from Druid, and it also blocked the other queries. We used clarity to identify the bottleneck and found that there were resource contention in the Druid broker. So we decided to create tiering for the brokers also and added routers to route the queries. So this is what we learned. The heavy queries that return large results may throttle the performance of light interactive queries. Our batch processing pipeline needs to both send flows to Druid and query configuration data from it. If this query gets blocked by another heavy query, such as the ML job, then the entire data pipeline gets blocked. We use tiering to create dedicated historicals and brokers for the configuration queries. Another thing we learned is Zookeeper. So Druid relies on Zookeeper for inter-service communication like task management or leader election. But unexpected issue may happen when Druid Zookeeper and metadata storage are down at the same time. For example, when there's a power outage or a network issue. So one thing we found was that the coordinator won't pull retention rules and dropped all the data in the historical. The workaround we found is to post a new rule through the coordinator API, so coordinator will be forced to sync with the metadata storage, and this will update its rules. Another issue we found was that the overlord is not posting tasks anymore, even though all the supervisors are running. The workaround for this is to restart the overlord service. We also tried to reset the supervisors, but that didn't help. Another thing we learned is about temporary files. So when spell to disk is enabled, the temporary files may not get removed from the disk in some scenarios. For example, when you are running a very heavy query and the query times out, the temporary files from that query will remain on the historical. In another scenario, when you are doing a very large ingestion, for example, a reindexing, and then some exceptions were thrown in that ingestion, then the intermediate persist will remain on the disk without getting cleaned up. The workaround we found is to clean up the temporary folders manually using a cron job. As we move our service to the cloud, we expect to see more challenges. Obviously, we will get more data and it will add pressure to Druid. Another thing is we will run multiple instances in shared nodes to save cost. This means multiple Druid services may run in the same worker node and it will compete for resources. Finally, we have a wish list. Overall, we want to see reduced resource consumption. As of now, almost half of our resources, including CPU and memory, are dedicated to Druid, and this makes it harder to add new applications without adding cost. We also want to reduce complexity. So each Druid service is a JVM, and JVM needs at least a few hundred megabytes just to get started. If we can combine some of the services, it will also reduce resource consumption. We want to remove Zookeeper dependency. Zookeeper costs additional resources and it has caused a lot of headaches for us. Systems like Kafka have already removed Zookeeper dependency, and we hope to see the same for Druid. On the ingestion side, we wanted the big indexer. It has been in experimental status for a while, but never got into production status. Now we want to have indexing tasks as Kubernetes jobs. So the middle manager needs to preoccupy a large amount of resources because it needs to have them when it runs heavy jobs like reindexing or compaction. However, those jobs may only happen once in a while and the resources are not always required. If the tasks are run as Kubernetes jobs, then resources can be allocated and released dynamically. On the query side, we want to see group-by-query optimization. We have seen queries taking a few minutes to run even when data is only a few hundred megabytes. That is because we are grouping on some high cardinality dimensions, but we want to see optimization on that side. Also, we want the ability to query from deep storage directly so we can save resources from the historical. So that's NSX Intelligence journey with Druid. Hope you enjoyed the talk. Thank you.